Hello and welcome to this video for Chemistry 30. This is the first lesson in the unit that I call Equilibrium Acids and Bases. For short, I call it the EAB unit. There's kind of two parts to this unit. There's an equilibrium part, which we'll start talking about today, and then there's an acid-base part. Now the acid-base part builds on the equilibrium concept, so that's why we start with the equilibrium concepts. So what is equilibrium? So it's important to note that when we have a reaction, reactions are often reversible. So even though when I write a reaction, I always show my reactants on the left-hand side and my products on the right-hand side of the arrow, I can actually write a double arrow. That double arrow represents the forward and reverse processes taking place. So as the products are formed, they can start to react with each other and remake the reactants that had disappeared. So the forward and reverse reactions will proceed at different rates. So at first, only the forward reaction will happen because all you have to start are the reactants. Generally speaking, we start with reactants as the only species present. So that'll be the fastest reaction. Now, as the products C and D are formed, the forward reaction starts to slow down, but the reverse reaction speeds up, and then at some point they become equal. That's where the term equilibrium comes in, okay? So my forward reaction again starts fast and is going to slow down. My reverse reaction starts at 0 and speeds up, and eventually the rates, this graph is showing the rates equal out. That's the point at which you've reached equilibrium in a reaction. Now, a system is said to be at a state of equilibrium when three properties are true. First of all, the rates, again, are equal. The macroscopic properties, such as temperature, pressure, concentration, and pH, are all constant. And the system is closed at a constant temperature, or we could also say it's isolated. Okay, so we're not adding any more substances to the system. We're not changing the temperature. Everything is now constant. Now this, for us, would appear that the reaction has stopped. The reaction has made as many products as it's going to make, and it's now done. But in fact, it's continuing to happen, but at equal rates. So it appears that nothing's changing, but the reaction is still taking place in the forward and reverse process. Now, there are three classes of equilibria. First of all, it can be something that we call reactant favored. A reactant favored we show by writing a less than 50% above the double arrow. This means that after the reaction has gone to completion, remember again though, at completion, it appears like the reaction has stopped, but it is still happening at forward and reverse rates. It's just that the amount of everything is now constant, okay? There will be now more reactants left over than products being produced, okay, when it is reactant favored. If it is product favored, above the arrow we put greater than 50%, and at that point, after the reaction is complete, there is more products than reactants left over. Okay, so we can compare the relative concentrations of everything. If there's more reactants left over at the end, then we say it's reactant favored. If there's more products left over at the end, then we say that it is product favored. The last type of equilibrium you can have is what we call quantitative, which is kind of what we always assumed our reactions to be, where all the reactants are gone and you're producing 100% products. In this reaction, you can actually use a straightforward arrow, only if the reaction is said to be quantitative. Now, there's something else that we are going to talk about today, which is called the equilibrium constant. So experiments have shown that under a given set of conditions, a specific quantitative relationship exists between the concentrations of reactants and products. Okay, so what that means is I have a relative amount of products to reactants. And this is actually our equilibrium constant is written as Kc, C standing for concentration, square brackets representing concentration. This is the generic formula for the equilibrium constant. Okay, it is the concentration of products relative to the concentration of reactants. So scientists have extensively studied the reaction forming HI gas because they're simple molecules in gas phase, so no solvent is necessary. When they mix different combinations of hydrogen and iodine to produce HI, they discovered that the same relative amounts of products to reactants was reached. Even though the equilibrium concentrations were different, the end quotient was the same. Okay, so the relative amount of products to reactants were the same. So this leads us to the law of equilibrium, which says that there's a constant ratio between the concentrations of the products and the concentration of the reactants at equilibrium. So if I have the following reaction, A plus B equals C plus D, the little a's and b's and c's and d's are balancing coefficients. This is how we are going to write our equilibrium expression. So Kc again, meaning equilibrium constant. The c's are the products go on the top, and the reactants go on the bottom. And again, they are raised to the exponent of their balancing coefficients. Okay, so some questions will just simply ask you to state the equilibrium expression. Some questions will ask you to actually calculate a numerical value for it. Now, before we get into that, it's important to know that Kc is constant for a specific temperature. If you change the temperature of your reaction, your Kc will change. We do not include units for Kc because it can get really complicated, so it's just a quotient of products to reactants. And this is important, we only include any substances that are either gas or aqueous in the calculation. If I have a reaction that has gas and aqueous species and also something solid or liquid, we omit the solid and liquid. Unless, here's an exception, all the states are solid or all the states are liquid, then we have to use them all. Okay? But otherwise, if there's any gas or aqueous phases in that reaction, I ignore any solids or liquids. Okay? Now, the Kc tells us the tendency of the reaction to favor the products. If Kc is greater than 1, it is a product-favored reaction. If Kc is less than 1, it is a reactant-favored reaction. It's important to note that Kc gives us the percent reaction, not the speed of the reaction. So not how quickly it'll reach the end quotient, but what is the end quotient. So a catalyst will not affect the equilibrium concentration. It only helps you increase how quickly you reach the end quotient. Note that if you have the Kc for a certain reaction, the Kc for the inverse reaction would be 1 divided by the Kc of the forward reaction. Okay? That's a question that I see come up on the diploma.
Please excuse the interruption. Any grade 11 students who are requiring picture retakes today, please head to the multipurpose room now. That's grade 11 students for picture retakes to the multipurpose room. Thank you.
Sorry, a little announcement there in the middle of the lesson. So here are some examples. Write the equilibrium law for the following reaction. We have nitrogen monoxide gas and oxygen forming nitrogen dioxide. Now you could be asked to write this equation yourself, or it could be given. Remember to balance it, okay? Now our Kc expression again is going to include anything that is a gas. It is products, NO2 gas, over reactants. So this is my product. It has a balancing coefficient of 2, so it's going to be raised to the power of 2. That is my only product. My reactant is NO gas, also raised to the power of 2 because it has a balancing coefficient of 2, times oxygen gas, which has no coefficient, so no power. And that's all this question is asking, to write the equilibrium law or the equilibrium expression. No numbers used to calculate, just show how you would calculate it if you were to. Okay? Next, write the equilibrium law for the following reaction. Notice how I have solids. Solids are omitted unless everything is a solid, but I have a gas. So my Kc expression is only going to depend on the concentration of the carbon dioxide. Okay, it's essentially over 1. So there is no solids included unless they're all solids. So this is only the CO2 gas. Next, we have water decomposing. Liquids are also excluded. So my Kc expression will be my hydrogen gas product raised to the exponent of 2 times my oxygen gas product with no exponent over again 1, or just like that is, because liquids again are also not included in Kc. Unless everything is a liquid, then you would include everything. Okay? Here is a sample diploma question. The equilibrium law expression for the reaction represented below. I have aqueous, so it'll be part of the expression. I have a liquid, so it won't. I have 2 more aqueous, so they will also be part of the expression. So as long as you're looking for the one that has products over reactants, excluding the liquid water, the answer is D. Okay, let's get some numbers involved here. So let's say we're told phosphorus pentachloride gas is being decomposed into phosphorus trichloride and chlorine. Prefixes tell us the formula for the compound. Phosphorus pentachloride, so that's PCl5, is decomposing into phosphorus trichloride, telling us it's a gas because it's molecular. And chlorine, remember, as an atom, is always Cl2 gas. Now this reaction balances itself out. Okay? So writing the Kc, it is the concentration of PCl3 gas times the concentration of Cl2 gas. Again, these are my products. They have no exponents because their balancing coefficients are 1 over my reactant PCl5 gas. Okay? Again, square brackets represent concentration. So in order to do this calculation, which we will do in this example with numbers, you need to know the concentrations, the moles per liter. Okay, so that is A, our equilibrium law or equilibrium expression. Then we are now given concentrations. This EQ here means the concentration at equilibrium. Now that is important for a little bit later on in the unit, because when you have a reaction, again, you're going to start with certain concentration of your reactants. They're going to go down and the concentration of products are going to go up, and we will look at a graph of that today. The numerical values that you use when you're calculating Kc has to be their concentrations once equilibrium is established. So once the concentrations become constant, okay? So to find our Kc, again, it was the PCl3, which is 0.014, times the Cl2, 0.014, over the PCl5, 4.3 times 10 to the negative 4. That again was the expression we just found in the previous A question. So 0.014 times 0.014 divided by 4.3 times 10 to the power of negative 4. Important to put that denominator in brackets. We get an answer of 0.455, so on. Now, how many sig digs can we have? There's 2, 2, and 2, because leading zeros don't count. So 2 sig digs would cut off right there. And remember, we do not put units with our answer. So the answer is just 0.46. Okay? Now, look at the following example. Find the concentration of the SO3 given the Kc. So I'm going to start by writing my Kc expression. These are all gases, so we can include them all. I have SO3, my products, raised to the exponent of 2 because of its balancing coefficient, over SO2, also raised to the exponent of 2 because of its balancing coefficient, times O2 gas. Now, if I put the numbers in that I have my Kc. My Kc is 85.0, given right there in the question. SO3 is what we're solving for. It's asking us to find SO3. So I'm going to leave it. You could label it as X if you wanted to. My SO2 is 0.500, and that one is squared. And my O2 is 0.500 to no exponent. So now to solve for SO3, I need to take my 85.0 and multiply it by 0.500 squared times 0.500. And that's going to give me my SO3 squared. Okay, if I rearrange for SO3 squared, it's going to be 85 times those two numbers. So 85 times 0.5 squared times 0.5 gives me a number. Again, this is my SO3 squared, right? It's raised to the power of 2. 10.625. So to get SO3 by itself, I have to get rid of the squared by square rooting. So when I square root that answer, I get a concentration of my SO3 gas at equilibrium to be 3.26 when I round it, moles per liter to my 3 sig digs, as everything else had 3 sig digs in the question. Okay, notice how it gave us a temperature because like I said, the Kc will change if the temperature changes. All right, so it's not used in the calculation, but it's just letting you know this is the Kc at that temperature. Okay, now we have another sample diploma question. You're given the following Kc expression. You're given Kc again. You're given the volume of the reaction vessel and the number of moles of two of the substances, the two reactants, okay? I have to, again, find concentration. Remember that C means concentration. The square brackets mean concentration. So the concentration of my C2H4 is 115 moles divided by 5,000 liters, okay? 115 divided by 5,000 gives us an answer of 0.023 moles per liter. And I have to do the same with my water vapor. 110 moles divided by 5,000 liters. You have to read the questions very carefully. If it gives you moles and volume, not concentrations, you have to find concentrations first.
Please excuse us in Hutch and any grade 8 teachers, please check your email regarding award recipients and send those people to the theater. Thank you.
Sorry, apparently it's a busy day for announcements. All right, so I am trying to find the concentration of my C2H5OH. I know my Kc. I know the concentration of CH4 is 0.023, and I know the concentration of the water vapor is 0.022. So when I solve, again, I need to multiply the 300 by 0.023 and by 0.022. And this is not squared. There was no exponent. So when I get that answer, that is the concentration of my C2H5OH, which is 0.1518 moles per liter. Okay, so that gives us an answer in scientific notation of B, 1.52 times 10 to the negative 1. Now, before we finish today, I just want to quickly go over graphical analysis. So, showing quickly how concentration versus time is used to calculate Kc. You have reached equilibrium when the concentrations become constant, when they stop changing, okay? So, for example, let's say I have SO2 reacting with O2 to make SO3. Notice how I'm starting with no SO3. Usually you start with no products. You start with a certain amount of your reactants. The reactants will go down in a curved line over time and then level out. The products will go up in a curved line and then level out. The point at which they stop changing is when equilibrium is reached. Okay, so for this question, equilibrium is reached at 20 seconds. And it's asking for the value of Kc. So again, if I write my Kc expression first, it would be my products, SO3 gas, raised to the power of 2 because of the balancing coefficient, over SO2 gas, also raised to the power of 2. I kind of made that line a little wonky there. And on the bottom is also O2 gas with no exponent. Okay? So to now solve for Kc, I need to use the values at equilibrium. Okay, so the values where the concentrations have leveled out. So my SO3 is 75 moles per liter, that one's squared, divided by SO2, which is 50, also squared. Make sure everything here is in brackets. My O2 is 25, so make sure we have a big bracket under that entire denominator. So 75 squared divided by 50 squared times 25. We get an answer of 0.09. Now everything looks to have 2 sig digs, so I need another 0 at the end. So the value of Kc is 0.090 and it is reached at 20 seconds. So when you have a graph, again, equilibrium is reached when the concentrations become constant. And those are the concentrations that you have to use in your Kc formula. I believe that is it. This is just the answer, which we just calculated. So thank you very much for watching this video.